Welcome to our second equilibrium tutorial. Today we're going to talk about Le Chatelier's principle. We've been talking about equilibrium systems and how equilibrium is a steady state, it's a dynamic state, and what Le Chatelier's principle is about is what happens to that steady state equilibrium system if we somehow stress that system. So we poke it, we do something to it that disturbs the equilibrium. What's going to happen? And what we find is if we apply certain kinds of stress to a chemical system, we change the relative rates of reaction. So at equilibrium, the forward and reverse reactions have the forward and the reverse reactions have the same rates, and if we apply the right kind of stress, we can make those rates unequal to one another. So that kind of disturbance, it does what we say shift. It shifts the chemical equilibrium. And it does that in a way that will resist the stress that was applied. So if we do something to the system, it's going to respond. And that response will result in a return to an equilibrium state. And what that new equilibrium state looks like will depend on what the stress is. So it's probably really good to look at some examples here. So first of all, if we change the concentration of something in a chemical system, you know that the rate of a reaction depends on the concentration of the reactants. So if we take a look at a system like this one here, we have decomposition of ammonia gas into nitrogen and hydrogen gas. And if we consider what would happen if we increase the concentration of a reactant. And in these examples here, when I say reactant, it could be something on the left side or something on the right side, because since the reaction is reversible, everything is technically a reactant. So for argument's sake, let's increase the concentration of nitrogen. So this line here is representing the moment where the stress is applied to the chemical system. And so let's say we have this nice equilibrium state. The concentration of the hydrogen, ammonia, and nitrogen are steady, so that's an equilibrium state. But at this moment in time right here, I'm going to inject some nitrogen into the system. So I'm increasing the concentration of nitrogen in the chemical system. Let's think about what that means. If previous to this point, the rates of the forward and reverse reactions were equal, but now suddenly I've got more nitrogen around, what that means to the reverse reaction here is really important. So for this reverse reaction to be occurring, it depends upon collisions that are happening between the nitrogen and hydrogen molecules. If suddenly I have a bunch more nitrogen than I had before, then this reverse reaction is going to increase in rate. So if this reaction, this reverse reaction, increases in rate relative to the forward reaction, what we end up with is a shift in that direction. So sometimes you might see this demonstrated in this way. We'll write a bigger arrow in one direction and a smaller arrow in another direction. So this equilibrium is going to be shifting to the left. Notice also that shift is resisting the increase. So we increase the amount of nitrogen, and as a result, the reaction is going to shift in the direction that will cause the amount of nitrogen to decrease. Let's take a look at what the graph might look like for that. So if we suddenly increase the amount of nitrogen, and the reaction is going to shift in a way to resist that, our reverse reaction is going to be able to go faster than our forward reaction. So some nitrogen is going to get used up before we return to a steady state again. So we added a bunch of nitrogen, and that nitrogen is going to get used up as that reverse reaction goes faster than the forward reaction. We're going to be producing more ammonia if we shift in that direction. So we'll see the amount of ammonia increase and then reach a steady state. And we're also going to be using up hydrogen. So if we're shifting to the left to use up that extra nitrogen we added, we're also going to use up more hydrogen. So that hydrogen amount's probably going to go down quite a bit. So notice the jump I made for the hydrogen is bigger than the jump for the other two. There are 3 moles of hydrogen reacting with 1 mole of nitrogen and 2 moles of ammonia in this reaction. So if we think about the mole ratios, these jumps need to be relative to those numbers, so I'll do my best to make that happen. If we took these concentrations before the reaction of hydrogen and ammonia and nitrogen and put them into our equilibrium expression, we would get our equilibrium constant. So if we knew what these numbers were and put them in here, we would get a value for KEQ for this reaction. If we took these values here that we reached after we applied that stress and plugged them into the equation, we would get the same number for K. So that's the beautiful thing about these equilibrium constants. As long as the temperature's the same, that system will push its way back to a steady state where this equilibrium constant expression is true. So that's kind of neat. If we do the opposite stress, so instead of increasing the concentration of a reactant, we're going to decrease the concentration of a reactant, we'll see the opposite sort of thing happen. So if we take a look at the same reaction again, we've got a forward and reverse reaction happening at the same rate, nice steady state, but at this moment where we apply the stress, I'm going to decrease the concentration of nitrogen in that moment. If I have less nitrogen around, now the reverse reaction can't go as fast if there's less nitrogen present. So if we lose some nitrogen, the reverse reaction is going to slow down. And what that means is the shift is going to happen in this direction in this case. By removing nitrogen, the equilibrium shifts in a way that will replace some of that nitrogen that was removed. And that's because the reverse reaction can't go as fast as the forward reaction, and so we're going to see that shift from left to right. So we're going to replace some of that nitrogen that we removed. Ammonia is going to be used up, so the concentration of ammonia is going to go down. And we're going to see the amount of hydrogen go up since we're shifting from left to right. And the same thing is true here that I said in the previous example. If you took these values and put them into your K expression, you would get a number for KEQ, which would be equal to the KEQ that you would get if you put these new values, these new equilibrium values into the expression. So that's how changing the concentration works. If we do something different, if we change the temperature, when we first talked about the equilibrium constant, I told you that it is dependent on temperature. So if we change the temperature of a system, we actually change the K value. In order to know what's going to happen in a system at equilibrium with a temperature change, we need to know whether we have an endothermic or an exothermic reaction. So it turns out our sample reaction here is an endothermic reaction, so we've got energy on the reactant side in this thermochemical equation here, I guess we could call it. So that means the forward reaction requires some energy input in order to occur. If we increase the temperature of our chemical system, what we're doing is we're allowing that forward reaction to go an awful lot faster than it did before. Now, since you learned about rates, you know that increasing the temperature will also increase the rate of the reverse reaction. But since this is an endothermic reaction, the forward reaction will increase in rate more than the reverse reaction will. By adding temperature, adding energy, the reaction is going to shift in a way that decreases the amount of energy that's present. So we're going to produce some nitrogen, and we're going to use up some ammonia, and we'll be producing some hydrogen. And when we reach this new equilibrium state, these values and these values put into the K expression will give you two different answers for K. So whatever K was before this stress occurred, it's going to be different after the stress occurs. If we do the opposite to our endothermic reaction, if we decrease the temperature, so we take away some energy, both forward and reverse reactions will decrease in rate, but the forward reaction will decrease more in rate than the reverse reaction. So what's going to happen is we're going to have a shift. If we decrease the temperature, we're removing some energy. The shift will see us replacing some of that energy that we have lost by decreasing the temperature. So if we shift in this direction, we're using up some nitrogen, we're producing some ammonia, and we'll be using up a bunch of hydrogen. So we might reach a new equilibrium state that looks like this. And again, the K value, the number that you get before and after, will not be the same as one another. Okay? So if we add energy, we're going to shift in a direction that removes some of that energy. And if we take some energy away, we'll shift in a direction that replaces energy. The last thing here we've got is a change in volume. So we have a reaction that involves some gases, and if you imagine a container that has some kind of a plunger, if we increase the volume, so I'm going in this direction, if I increase the volume of our container, that means we lower the pressure, so we lower the pressure and we lower the concentration of the gases that are present, all of the gases, so the reactants and the products. If we lower the concentrations, that means we're going to be lowering the rate, the forward rate and the reverse rate. But it's not equal. The effect on the forward rate is not the same as the effect on the reverse rate. If we decrease the pressure or the concentration of these gases, what's going to happen is we see a shift in the reaction towards the side that has more molecules. Because if we shift in this direction, there's a couple ways to think about it. We create more molecules. Okay, if we look at this reaction, there are 2 moles of molecules on the left and 4 moles on the right. So shifting in this reaction creates more molecules. It increases the pressure a little bit, so it resists the change. And that's because the rate of this reaction is dependent only on these 2 molecules of ammonia. The reverse reaction is dependent on 4 moles worth of molecules, if you think about it that way. So the decrease in rate is going to be greater for the reverse reaction than it is for the forward reaction. So in the moment that the concentration change happens, we're going to see a drop in all of these values because we've increased the volume, so we've decreased the concentration of everything in that moment of stress. And then the result is that we're going to produce some nitrogen, and we're going to produce some hydrogen, and we're going to produce some ammonia to respond to that stress. So here, before and after, your K values should be equivalent to one another. K before the stress should be the same as K after the stress because we haven't changed the temperature. Our last example then, if we do the opposite, if we decrease the volume, that'll increase the pressure and the concentration in the container. So we'll be increasing the concentration of hydrogen and ammonia and nitrogen by decreasing the volume of that container. That pressure increase is going to be resisted. So we're going to see a shift to the left in this case where we've got fewer molecules on the left side. We'll see a shift towards the side with fewer molecules, which will resist that pressure increase and result in decreasing the pressure inside the container. So if we shift away, we've got a decrease in hydrogen concentration, a decrease in nitrogen concentration, and an increase in ammonia concentration. Okay, something like that. And again, the K value before and the K value after are the same because we haven't done anything to the temperature. By increasing the pressure and the concentration, we do increase the rate of both the forward reaction and the reverse reaction, but the reverse reaction, that rate increases more than the forward reaction since it has more molecules that need to collide. There are 2 things that don't have any effect on equilibrium. The first is adding a catalyst. Catalysts change the rate of a reaction, so how fast it goes, but it will not change the equilibrium position. And then also we could increase the pressure inside a container by pumping some inert gas into it, so something like helium. So if we put helium gas inside the container, we could increase the pressure. But that doesn't increase the number of effective collisions we have, so it doesn't actually do anything to our equilibrium. Here are some questions you can take a look at before class, and Take your time with them and let me know how it goes tomorrow.